first of all, I would like to start by giving a little bit of love to the tropical forest. And I start by saying, why should you care about the tropical forest? And even if you are here in Idaho. So first of all, it provides a lot of ecosystem services that we benefit from. For example, climate change. If you're here in Idaho, maybe you're thinking about the 100 Fahrenheit degrees we are going to reach next week. And we have also ecosystem services of water regulation. It's a biodiversity reservoir. It serves as provisioning for thousands of families. And also it regulates nutrient cycles, which we really need for agriculture. So we need it. But the problem is that if you look at this graph, in which we have the forest area as a proportion of total land area in the x-axis, you can see that at least in Latin America and the Caribbean, we have a pretty steep decrease between 1990 and 2010. And those are bad news because that means that we have lost all of those ecosystem services we were talking about. And it actually will be pretty nice if we can get them back, right? And that's why we are having all of these initiatives in Latin America that are trying to restore and bring back those ecosystem services. And we actually know that we can bring them back because we have done some exploration and there is a lot of potential to get the carbon sequestration and all other ecosystem services. The thing and what all of these has in common, bringing back the forest and also these flows of ecosystem services, is that they are large scale processes. And they are large scale processes that depend on individual trees and people. And that's where we get the tree demographics. So we care about what is going to happen with these individual trees because we care about their recruitment, their growth, and their survival. So that's why we need to upscale them. So we know that we can capture these large scale patterns using remote sensing. And we also know that we can capture the individual ones, the individual trees using field sampling. But the way of bringing them together is process models. And that's what my thesis is about. This is all I want to do. I want to bring together this remote sensing, this individual trees information, and link it together using modeling. And that's why I have these 3 dissertation chapters. So in the first one, I'm going to talk about how can we upscale predictions of recruitment in tropical landscape. Then I'm going to talk a little bit about methodology and some challenges that I found when I was doing my first chapter. In this second chapter, in which we are going to talk about Bayesian models for spatially explicit interactions between neighboring plants. And lastly, we are going to go back to our tree demographics, and we are going to explore mortality and its drivers on a tropical agricultural landscape. So let's get to it. First of all, I would like to introduce Panama. So Panama is here in between North and South America. And on the right side, you can see a map of exactly where is my study area. That's Los Santos. So a little bit of a story and a little bit of context about Panama. So 3 million years ago, we had North America and South America coming together, and we had a huge mix of species, and we increased a lot the biodiversity that we have in this area. So this is a pretty important hotspot of biodiversity. Then the human decided to open again this canal like this way. And right now it's one of the main sources, like the main economical activities in Panama. And I'm going to talk a little bit about the area that I care about, Las Tablas. So here we have a map of the economical activity in 1981. And the main activity in this area is cattle ranching. And these have been happening since a really long ago. And the thing is that because of land productivity exhaustion, what we are getting is that the Panamanian ranchers are moving towards the Iberian. So we are having soft movements. And the ones that are still there are the ones that are, well, this is a title in the news in Spanish. It says Los Santos is on its way of industrializing its cattle ranching. So that means that we are having some people that is like becoming more intensive, but at the same time, we have some other ranchers that want to make their land more harmonious and have some sustainable land management practices. I know that Pro Ecuador and LP are there down there helping. And then we have an increase of tourism in Los Santos. That's what this title of the news means in Spanish. And all of this together has created this heterogeneous landscape in which we have riparian areas with trees, we have some secondary forest, we have pasture areas, but we also have some touristic areas pretty close to the beach in which we are having a lot of growth of infrastructure. So if we take a look at all of these contexts, we can find that there is a great need for restoration in Panama because we want that productivity to come back. It's a hotspot of biodiversity, and also because they depend a lot on their water. First, because the canal needs to have the right amount of water. You don't want to have too low levels or floodings on the wet seasons. And then because cattle ranching depends a lot on water, and actually in the area where I'm working, the dry season is pretty hard. So they have a lot of problems with drought. So that's why we have initiatives like Alianza por el Millón. That's an initiative to restore 1 million hectares on Panama. And this leads us to my third chapter. So why do we want to upscale recruitment to landscape scales and what it has to do with all of this? Well, the first step towards natural regeneration is actually getting some recruitment. And natural regeneration is one strategy that we can use to increase tree cover. Another one is tree planting. So tree planting is you go to the field and you plant some trees. The problem is that you need to get the trees, you need to get the seeds, and you need to get the people to go there. So it's pretty expensive. Well, natural regeneration, because it's going to grow by itself, is pretty cheap. The problem is we don't really know where it's going to happen. And to illustrate this, I'm going to play a game that maybe you have already played with me. You have been one of my presentations, and is where do we plant trees? So imagine that you're a landowner and you want to have all of this land full of forest in a few years, but you only have money to plant trees in one of these properties. So you have to choose, and the other one is going to have to do it by itself. So raise your hand if you will use tree planting in this parcel. Okay. Now raise your hand if you will do it in this other. Okay, so after a few years, natural regeneration happened in this side. And that means that if you planted trees there, you're going to have no trees on the other side and you didn't meet your goals. And probably you're thinking, yeah, well, Cristina, this is an image, like this is not enough information. We could have gone to the field, get some data, do some models, and you're totally right. I totally agree with that. But the thing is that these two parcels are just these teeny tiny a spot in 23,000 hectares. And given the size of the degradation and our goals that are globally 150 million hectares and in Panama 1 million hectares, we need to be able to know what is happening at landscape scale so we can plan better. We cannot go one by one to each of these parcels and just get the data. That will be impossible. So that's why I'm doing this. And one way in which we can do this and get these large-scale ecological process is using remote sensing. And I'm not the first one trying to do this. So there has been previous studies that have helped to know a little bit more about this and have used remote sensing. They have used forest cover as a proxy for seedlings, for seed sources. And then they have tried to link that with the recruits. The recruits are here, like the seedlings here. These things that look like green flies. So, and what they found, some of them didn't found any kind of effect, and some of them found a positive effect between seed sources, so the forest cover, and recruits. So the question is, why are we finding this variability between studies? What is going on here? And well, if we look at the literature, we might think that, well, having a parent tree, so knowing what species do we have in the forest cover, and if we have the parent tree of those recruits in the forest cover, might be something important. And the other part is, well, these are pretty degraded lands, and they have been used. They are being used by humans. A lot of human-nature interaction. So probably land management is something that is important in this land and for this recruitment. So what if we actually knew the species and the land management at landscape scale? Luckily, and thanks to Sarah Grace and Greg Asner, and all the co-authors from their paper, we actually have a map. All these black dots that I just overlaid are all the tree crowns classified by species that are in these 23,000 hectares. So we actually know the size, where, and the species of each tree in 23,000 hectares, which is actually pretty impressive. And then from these species, we selected 5. We selected the 5 that were the best classified. So with an F-score of more of 0.7. F-score is an accuracy measurement that is going to tell us how well from 0 to 1 we classified the trees. The first species that we selected is Birsanima crassifolia. People like it a lot for eating. It's an edible fruit, and that's why it's also animal dispersed, and it's a mid-successional species. Then we have Wathumolmifolia. The fruits are tasty and sugary for the cows, not for us. And and farmers use it for as fodder for the dry season. And it's an early successional species that is dispersed by the cattle. Then we have Cedrela dorata, a pretty valuable timber species, and that one is dispersed by wind. And also, it's a mid-successional species. Then we have Calicophyllum candicium, wood fire species dispersed by wind, and late successional species. So this species likes the forest. And then we have Enterolobium cyclocarpum. This is another species that the cows like, so it's pretty useful as food during the dry season. And it's early and late successional species, and is dispersed by the cattle again. So you can see that we have a diversity of the species with different traits, with different dispersal syndromes and different uses. Then to characterize what are the land management, we use some cadastral data, so property boundaries. So we might not know what is going to happen exactly here in this parcel, but at least we know that the land management from one parcel to another one is very likely to be different. So we can characterize this variability on the landscape. So now we have all these data, which inspire these 3 questions. So the first one is, can we use all of these data to improve the tree recruitment predictions at landscape scale? The second one is, does land ownership actually influence tree recruitment abundance? And the last one is, does the effect of neighboring trees on recruitment abundance vary between species? So we have our remote sensing data, we have our questions, and now we are missing our response variable, our inventory data. So I gathered all my stuff and put everything into backpacks and went down to do some miles or kilometers in slopey areas and pretty sunny areas. And what we collected was the location of seedlings and saplings from 0.1 to 10 centimeters dBH. And to do that, we used a tablet and a BAT-ELF GPS. And we collected this data in 100 meters transects that are divided into 5x5 plots. And we located them randomly on the landscape. So the data in the end looks something like that. So if this is our plot of 5x5 meters, this is our response variable. So how many seedlings do we have? And then to represent the parent trees and the rest of the forest, we have the crown area of conspecific and heterospecific trees. Conspecific trees are trees that are the same species as the recruits, and heterospecific trees are trees that are a different species than the recruits. And then we sum it up the crowns separately for conspecific and heterospecific trees. Then from the map, we also got the species identity and the property identity from the cadastral data. And when we were looking at our data, we realized something, and is that we have these transects, and we are having a lot of areas where we don't have a lot of recruits. And that might be possible because recruitment is something that is rare on this kind of landscape. There is a lot of disturbance. So it's an ecological process. And we have a data reaching zeros because of an ecological process. And that's why we decided to use a zero-inflated model. So a zero-inflated model is a model that has 2 parts. One that is going to take care to tell us where natural regeneration is going to happen and where it's not. So in green, will be an example of how it will predict we have recruits, and in white where we don't. And once we know where, this second part of the model is going to calculate how many recruits we are going to actually have. So after analyzing the data, these are the results. So for question 1, the answer is yes, we managed to improve it compared to the intercept. And we actually got a mean absolute error. The mi here is the mean absolute error of 0.17. And what does it mean? Well, it means that if we predicted in a 5x5 plot that we are going to have a given number of recruits, we might be wrong by 0.17 more or less, which is actually a pretty good measurement, right? The next question is, does land ownership influence tree recruitment abundance? And the answer is yes. So our best model from all of the ones that we tested with all these variables had property here in blue as a random effect in the intercept, and also for the fixed effects that we included. So why these predictions are useful? Well, a way in which we could apply this is if you look at property 1 and property 4, we could actually project this recruitment into maps. In this, we have in darker green the areas where we predict more than one recruit in every 5x5 meters. And we could do the same for example, Wirsonima crassifolia. So if, for example, the property owners of property 1, they would like to have calicophyllum in this area of their parcel, well, I'm sorry, we will have to plant trees because it's not going to happen. The other, for example, if the owners of property 4 would like to have some calicophyllum here, well, like we can do it cheaply because it's going to grow by itself, so why to bother? So great, you might have to fence because of the cattle, but at least we know that it's going to happen. So that's how we could use it. Then for question 3, does it vary by a species? And the answer is we found that conspecific, so trees from the same species as the recruits, contribute way more than the trees that are different than the recruits, so heterospecific trees, to recruitment. And we can see that in these two graphs. So in these two graphs, in graph A, we have the number of recruits against the number of average size tree crowns. That's the second part of our model, so calculating the number. And then in graph B, we have the probability of recruitment against the number of average size tree crowns. That's our first part of the model, presence, absence of recruits. And we can see that for both, the slope of conspecific trees is way steeper than the one for the heterospecific trees. And actually, for the conspecific trees, we have a negative, conspecific negative density effect. So this could be one reason why studies are finding these variability in results. So maybe if you don't have the right amount of conspecific trees inside of your forest cover, you are just getting the signal of the heterospecific trees, which have a pretty low effect on the recruitment. So in conclusion, we can use a species-specific map and cadastral data to improve our predictions of tree recruitment. Also, the fact that we can differentiate between conspecific and heterospecific trees inside of the forest cover is pretty important. And lastly, there is a great potential to use this to inform different land management and restoration projects. And this leads us to chapter 2. So while I was working on chapter 1, I realized a few problems, and actually that was something that happened in general in our lab. We were all at the same point in which we had this same problem. And I'm going to, well, there were several problems, but I'm going to explain the most important one for this chapter, and is that these kind of models can have great amount of data. And to illustrate that, I'm going to use this example. So imagine that you have 3 plants and you want to know what is the interaction between them. And you want to know how it varies because of their distance, how far they are from each other. And the way in which you put the data in these kind of models is a pairwise matrix. So we have a diagonal with zeros because the distance between a plant to itself is 0. And then we will have to include the distance from plant 1 to plant 2, the distance between plant 1 to plant 3, and the distance between plant 3 to plant 2. But what happens if we add a 4th one? That means that we have to include its relationship with the other plants. And that can make these kind of matrices huge, because every time that you add one individual, you are increasing the size of your matrix in a series of square numbers. And that means that with very few individuals, you can get huge matrices that are pretty hard to handle. And I don't think that this is a problem that I only have, because plant interactions are pretty important. So plant interactions are relationship between plants, and they can be positive if they are facilitation, or negative if they are competition. And they affect the growth, survival, and recruitment. So the same as the relationship between conspecific trees and the recruits was pretty important in my last chapter. Being able to know how to modify the survival, growth, and recruitment of trees might be pretty important for different disciplines, like, for example, silviculture or agriculture. You want to modify those so you get the maximum yield out of it. So that's why this is important. And that's why our objective was to create some guidelines for ecologists on how to parameterize spatially explicit neighbors interactions using STAN. So STAN is a Bayesian software. That's the one that I have been using, and it has several advantages, like it's pretty flexible, so you can use nonlinear equations, but also it has a lot of metrics that are going to allow us to know that our model is working and our model is exploring the probability surface properly, so we are getting a proper answer. So going back to our problem, we have a very big matrix, and what we did is to use this like pretty simple ecological principle. That is, plants that are far interact less. If they are very far, they don't interact. So we use effective neighbor radius in this case to illustrate it. Let's say that it's 5 meters. So that means that we get way less data. That's pretty good. But the problem is that in STAN, you cannot include NAs. You have to include zeros. So again, we have a problem. We have, again, a lot of data, and we have a sparse matrix, which is something that is not very efficient to use. So, we use a range matrix, and a range matrix is just a matrix that has an even number of values in its rows and its columns. So this is great for data storage, but you cannot do linear algebra with it. And that means that you cannot put it inside of the model directly. You have to find a way to translate it. Luckily, in STAN, we have the segment function. So what the segment function does is, if the predictor matrix is our sparse matrix, it puts all the non-zero values into a vector. And then we have another two vectors, MVB and POS, that are going to tell us what was the original structure of our sparse matrix. And in that way, the segment function is going to translate it to the model, so we can do that linear algebra that we need for the model. So that's the way it works. But this is very nice. The explanation is great, but proof. So we simulated some data. And what we simulated is some trees in an X and Y coordinates that you can see in this graph. And the size of each of these dots is the size of the trees. And what we wanted to know is how the growth of these trees is affected by the neighbor plants. So we constructed the model, and we actually wanted to know how actually having different levels of compactation of our range matrices was going to affect this efficiency. So we tested it with different effective neighborhood radius. But we simulated the data with 10 meters. So that was our true value for the neighbor, for the effective neighborhood radius. And these are the results. So in this graph, we have the time divided by the effective sample size. So how long the model took to run, divided by how well it performed. And then we have the effective neighborhood radius in the x-axis. And we can see that the range matrix performance was more efficient than the sparse matrix for all of them, but for the 10 meters, which is the true neighborhood radius. Effective neighborhood radius. And the thing is, like, well, you don't usually know a priori when you get your data what is going to be your effective neighborhood radius. You can or do experiments to see when your plants stop interacting, or you can just, as we did, fit a bunch of models with different effective neighborhood radius, and then do some model selection. So since you're going to have to fit all these models, better to do it fast so you don't take that long. So maybe better to use the range matrices for this. So simulations are great, but they are also data that we are simulating, and we need to demonstrate that we can apply this to real data. So we do one of Colvin's papers, a case study in which we were looking at the effect of distance to parent tree on seedling abundance of invasive strangler pigs. So we ran both models, the range matrix and the sparse matrix, and we found that the ragged matrices had a 72% more efficiency than the sparse matrix. So pretty similar results as we got with the simulation. And the results were in this graph. You can see them in this graph in which we have recruitment against the distance from parent tree. You can see that recruitment was decreasing with the distance from parent tree. And we got similar results for the sparse matrix, the ragged matrices, that with very similar uncertainty, and also comparable to the original study. So in the end, what we got out of this chapter, first is that ragged matrices can be pretty useful for like fitting these kind of models. And also that if we can optimize these kind of models and work with this huge amount of data, then we can like do way more analysis and explore way more, especially species interactions between neighboring plants. And that after this, we are going to go through chapter 3. So chapter 3 goes back into the demographics. And well, you know, it's pretty nice that the forest is growing back, but we also want to maintain what we have there, right? Like all the trees that we already have there. And actually, we want to do that because they are pretty important. They maintain agricultural productivity, they store carbon, they conserve biodiversity, and they are also an alternative source of income for landowners. The thing is that studies have been warning us that we are losing those trees. They are decreasing on the landscape. And there are not that many studies that are telling us why is this happening, and even less on tropical forests. So that inspired these questions. What are the drivers of agricultural trees mortality? And we have some theories from literature. So it could be anthropogenic factors. So we know that large scale human actions like land use change, including land intensification and tourism can have an effect, but also the individual scale processes like farmers preferring some species on their land than other farmers. Then we have the tree characteristics, so the fitness of the tree. And then we have the topographic variables, so how the landscape looks like. So from the anthropogenic factors, the ones that we saw that we could use at landscape scale to characterize this were the distance to roads from the trees, the forestry cover, and that's going to tell us if our tree is in the middle of the forest in a riparian area or if it's in the middle of an agricultural pasture. And then we have the size of the parcels. About the tree characteristics, we wanted to know the size of the trees. Yes, because bigger trees might be better at competing against other trees, but the problem is that they're more prone to carbon starvation and hydraulic failure. And the same happens with the tree crown. So if you have a pretty big tree crown, you might be able to get more sand, but at the same time, you have more evapotranspiration surface, so you're more in danger of hydraulic failure. And then we have the topographic variables. So you can see here that Panama is not, well, this area where I'm working is not flat. It has a lot of hills, so it might have an effect. So we have elevation that might be affecting how easy it is to access this area. And then we have site exposure. Site exposure is a measurement of how much solar radiation are these areas getting. And because we're including the slope and the aspect, we know also how steep it is. So if we have so many theories, if this is so important, why no one has ever done this before? And the thing is that when trees grow, they die pretty rarely. So there is a point in which they reach a 0.99 or even higher survival. And that means that if you go to the field and you collect mortality of 100 trees, maybe one of them died. And that means that if you actually want to collect enough data to characterize the mortality and its drivers, you need to collect a huge amount of data on trees that will be pretty hard to get on the field. And that's even tougher in agricultural landscapes where the trees are pretty sparse. So again, our favorite resource, we used remote sensing to solve this. In this case, what we did is we got Google Earth Pro because it's free, has an amazing spatial and temporal resolution. And we overlay the tree crown that from previous map that we used in chapter 1. the one in which we know where all the trees in 2012 are. And we check it if they are dead or alive. So the 2 yellow one in the corner seems to be alive. The red one in the middle seems to be dead. And the red one in the right corner seems to be alive still. So that's how we classified it, as simple as that visually. But we wanted to know how well we did. So we went again to the field and looked for some more trees. So we went to the trees, make sure that they were fine. If they were dead, they were alive, give them a little hug because they are doing great and they are awesome. And then, well, we wanted to know how well we did. And remote sensing is amazing, but it's not perfect. So we're going to play another game. So again, this is a Google Earth Pro image of 2019. And then we have on the top of it, the silhouette of a tree that we know that was alive in 2012. So the question is this tree dead or alive? Raise your hand if you think that it's alive between 2012 and 2019. Yay, field data says that it's alive. Okay, then what about this tree? Raise your hand if this tree is alive. No one? Well, you're right, it's dead. Okay, what about this tree? Is this tree dead or alive? Raise your hand if you think that it's alive. It's dead. So you can see that it's pretty hard, and we actually evaluated ourselves to see how well we did, and we got an F-score of 0.92. So again, the accuracy measurement of how well we did in the classification between 0 and 1. So it was not bad, but we wanted it to be better. And the way in which we corrected this is using a detection probability model. So we were interested on the survival given the observed data. And what we wanted to know is Z1, that is the true state of the tree. But the data that we had is the observed state of the tree detected using remote sensing. So we used the field data and the remote sensing data to calculate these P11 and P10. So those are the probabilities of a tree being alive, being classified as alive when it's alive on the field, and the probability of a tree being classified as alive when it's actually dead. So that's what we use to correct it and get the actual psi, and 1 minus psi, that's the probability of it being alive or the probability of it being dead. So we needed a part of our model, we needed the rest of the variables. So again, from this map, we collected the tree crown size, the species, and also from the LiDAR, we got the height of the trees and also elevation, slope, and aspect. Then from the cadastral data, we got the size of the parcels and the parcel identity. And from a roads map, we got the distance between the trees to the roads. And these are the results. So here we have the posterior distributions of the effect size of these variables on mortality. And what are these? Where these are telling us how likely it is that these variables have an effect. So that means that the more centered they are into this black line, the 0, less likely they are to have an effect. So I'm going to explain the ones that had the strongest effect. In this case, we have elevation with a 97% of probability of having a negative effect on mortality, which means that we are having higher mortality on lower elevation areas compared to higher elevation areas. And that might be because of accessibility. So lower areas might be flatter and therefore more attractive for cattle ranching and agriculture, while reaching higher elevations is a bit harder for that. Then we have distance to roads with a 94% probability of having a negative effect on mortality. And this might be because, well, if you're going to log a tree, why would you go super, super far if you can just log it super close to the road, right? So that's why it's more likely, but there is something else going on. So when we were down there, we noticed that around the main road, there was a lot of infrastructure construction because of tourism. So land use change here is playing a role. And then we have tree density that had a 97% probability of having a negative effect on mortality. And that's because probably trees that are inside of the forest and the riparian areas are more likely to survive. And that might be because, for example, it's forbidden to log trees around the rivers because you have to keep 50 meters around, but also because trees that are isolated inside of the agricultural pastures are more at the mercy of these land use changes, as well as other ecological factors, like, for example, storms or drought. So in the end, our conclusions are that high-resolution remote sensing can inform conservation of trees in agricultural landscapes. Also, that accessibility and land use change might be driving tree mortality, and these are kind of like good news because it's something that we can use policies and land management strategies and training programs to try to palliate this kind of tendency and avoid losing these agricultural trees. So now is the moment of the overall conclusions. So the overall conclusions are that we can use high resolution remote sensing to characterize these large scale patterns that depend on individual trees, like, for example, natural regeneration, or, for example, the decrease of trees in the agricultural pastures. But we need to use novel and optimized modeling methods so we can actually get as much as possible from this amount of information that high spatial resolution remote sensing can offer. So now is the time for the acknowledgements. So I would like to first acknowledge my committee, Dr. Jody Brandt, Dr. Kelly Hopping, and Dr. Pedro Rancalion, for all the work that they have put into me and this thesis. I will also like to thank the biology department. The faculty has been amazing and pretty inspiring. They have offered a lot of opportunities to me, like being a student representative for the hiring, and also to the people on the front desk, especially to Nicole, to Brittany, and to Adil. They have made my life way more easier, and I love them because of that. Then we have our collaborators, Sarah Grace, Stephanie Bowman, Trev Asner, Jefferson Hall, Peter Seidema, and also the people that provided, well, the organizations that provided some funding for this, including the Smithsonian, NSF, and GEM3, and also the organization that provided support for the field, Pro Equasuero. And of course, I would like to thank Trevor. So I think it was Jody, the one that said that in this picture, it looks like I'm here doing my things, happy, but Trevor is down there just in case I fall. And I guess that's kind of a little bit of the style of Trevor. He's an amazing mentor, and he's there whenever you need it. He gives you pretty good guidelines, and he also lets you do your thing, which is pretty amazing. Always on Twitter, I hear a lot of people saying that their PhDs were awful, they were terrible, and that they hated them. I'm not going to lie, it was hard. But thanks to Trevor, it was a moment in my life that I'm going to cherish for the rest of it. And well, thank you so much, Trevor, for making this an amazing experience. Then I will also like to thank the people that helped me on the field, including Mario Bailon and all his help with the species identification. I will also like to thank my lab. And well, Yori is not from the lab, but I wanted to include her here because she has been one of the faculties that I have interacted the most. And she's been amazing. She always has great advice on career development. She has great advice on writing, on anything. And she has been there for me as a person and as a mentor for my whole PhD. So Jody, you're an amazing person. Thank you so much. And then I would like to thank all my friends that took me out of work, especially the Basque ones, the ones from the Basque country. Also the ones that took me out to do some outdoor activities. If you have climbed with me and you are not in any of these pictures, it's because I didn't have a picture with you. Then I would like to thank my friends from Madrid for all of their support and still liking me, even if I'm never there. And I would like to especially thank my family because of all of their support. And well, they are the ones suffering the most this PhD since they only get to see me in summer and Christmas. So thank you so much, family, for all of your support. And lastly, thank you so much for being here to all of you. I will answer any questions y también puedo responderlas en español. Thank you so much.